Hello. So, standard conditions. We've talked about standard conditions before. Remember when we've seen that not symbol? That's when something is in its standard state. So, we're talking about different substances, right? If it's a gas, that means it's a pure gas. It doesn't have anything else in it at 1 atm of pressure. If it's a solid or liquid, it must also be pure in its stable form at 1 atm of pressure and the temperature of interest, which we usually say is 25 degrees Celsius or 298 Kelvin. If it's a solution, it needs to be at a concentration of 1 molar. So how do we use this? What does this mean? Well, let's move on to the third law of thermodynamics. So the third law of thermodynamics talks about the absolute entropy. That is the amount of energy a substance has due to the dispersion of energy through its particles. So how much energy do we have based on the arrangement of our particles? Well, we had our Boltzmann distribution equation earlier. It talked about entropy. It said W, right? How many ways can we rearrange things? Well, a perfect crystal can only be arranged in one way, right? It is ordered, so its W value equals 1. So for a perfect crystal, and if we are at a temperature of absolute zero, so 0 Kelvin, the entropy of this crystal will be 0 joules per mole Kelvin. So this is the only substance that will have a 0 joule per mole Kelvin. This is the absolute entropy of this crystal. Entropy, we said, is always increasing. It is always positive. So the only one that will ever be 0 would be a perfect crystal. Everything else does have some entropy associated with it. So if we talk about entropy change of chemical reactions, in which we have the final state is more random than the initial state, which we talked about, right? If it goes from a liquid to a gas, it's going from more ordered to less ordered, then we know our delta S of our system is positive. Therefore, our entropy change is favorable for our process to be spontaneous. If our final condition is more ordered than our original condition, then our delta S of our system is negative, and it is unfavorable for the process to be spontaneous. So we would say it is non-spontaneous. We can calculate delta S of our system or delta S of our reaction by saying that we can take the sum of the moles, the number of moles of our products. This is our entropy at, right? This is our standard state entropy because it's got that not symbol. So we can do the sum of our products minus the sum of our reactants. We've done equations that look like this before last semester. So our absolute standard entropies would be a S naught. That means we are under standard state conditions. So we're at, 1 atm, we're at 1 molar. They are pure substances. These are known values. You would be given a table for these. Entropy is an extensive physical property. So that means it does matter how much we have. If we increase our amount of matter, we will increase the entropy. So the entropy is only per 1 mole. If we had more moles, right, our entropy would increase. So it is for 1 mole of a substance at 298 Kelvin for some particular state. So if it was a gas, it would have one value. If it was a liquid, it would have another value. If it was a particular allotrope, so the difference between diamond and graphite. If the molecular complexity changed, if it had a ring structure or a straight chain of carbons, maybe. Particular molar mass, a particular degree of dissolution. These entropies are all different based on what we're looking for. So you would be given a chart. It would tell you what you need. So our states, take a look at this. Does this make sense? Well, we know that a liquid, in comparison to a gas, a liquid is more ordered. So its entropy is lower for that of a liquid than it is for a gas. That should make sense, right? So our standard entropy is going to be higher for a gas. So if we had solid, our solid, you should be able to tell me, is going to be less than 70. right, joules per mole Kelvin, because a solid is more ordered. So here is a table of standard entropies. We have, some gases, some liquids, some solids. Mostly, for the most part, right, these solids are lower entropies than our liquids or our gases. It does change if you look as we keep going down the list. These are more complex molecules. So these more complex molecules, obviously, they're going to have higher delta S values. Apologize. Also, the larger the molar mass, the larger the entropy. We're not going to get into this exactly in this class, but if you think about it, there are more energy states, right? N equals 1, N equals 2, N equals 3. So we are allowed to have more closely spaced electrons that allow for dispersion through our energy state. So our electrons can jump to different energy states, and so we end up having a higher entropy with our higher molecular mass molecules. Also, our allotropes, right? The difference between diamond and graphite. Well, diamond is highly ordered. It has all of these bonds that are holding it together. It's very constrained. So it has a very low entropy. Whereas graphite, right, it doesn't have any bonds between these two carbons. It's just sheets of carbons. And so it is less constrained and it has a lower entropy. A higher entropy. We can also look at more complex molecules, so argon and nitrogen monoxide, right? They're both gases. Their molar masses are pretty similar, right? Argon's a little bit higher, but argon has a delta S that is lower. That is because argon is just one molecule, right? One atom by itself, whereas nitrogen monoxide, right, there are two atoms together, and so it ends up having a higher entropy. We look at the molar mass down here of these two molecules. As you can see, they're almost identical, but the entropy of C2H4 is much higher, or is higher, right, than carbon monoxide. This is because we have different types of rotations, vibrations. We can have movement of an NO molecule, right? It can translate in the XYZ direction. It can rotate. It can vibrate back and forth. So all of these different motions take into account the fact that its entropy is going to be higher than that of just pure argon. If we dissolve something, so we know, right, a solid is going to have a lower entropy than that of something that's dissolved. Because when we dissolve this, if it's aqueous, it breaks apart into its ions, and so now it is more disordered. So a dissolved substance will have a higher entropy. So we can calculate the standard entropy change as the sum of the moles of our products times their entropy in their standard state of the product minus the sum of the moles of the reactants of the entropy of our reactants in its standard state. Remember, we did enthalpy before. The enthalpy of formation of any element before was 0 kilojoules per mole when we had an absolute entropy at 25 degrees Celsius. We know, though, that our S values are always going to be positive, right? Because there's always going to be some entropy of our system. We will not ever have a 0 like we had before with enthalpy. This is because the only 0 we would have would be a perfect crystal at 0 Kelvin. So let's take a look at this one. Example 18.5. Calculate delta S for this balanced equation. So here they gave us all of our reactants and products. They gave us our delta S values, or our S naught values. What we can do is we can write our equation. We're trying to find delta S of our reaction. So delta S of our reaction is going to be the sum of our products minus the sum of our reactants. So once you have all of the values in the chart, you can go ahead and write your equation. So S is, we said it's going to be the sum of the moles of our products minus the sum of the moles of our reactants. So what we're going to do, we're going to look first. So the first thing we have is we're going to look at our products, right? Because our reaction is products minus reactants. So N of our product. So our first one, we have NO. We have 4 of those. Okay, so those 4 we're going to put down here. We're going to multiply that by our S of NO. We're going to add that to, we have 6 moles of water in the gaseous form. So we're going to multiply that by 6 times the enthalpy or entropy of our water. So that would be the sum of our products. We're going to add those two together. Minus, then we're going to do this for our reactants. So we have 4 ammonias, so 4 times the entropy of ammonia, plus 5 times, right, because we got 5 moles of oxygen, 5 times the entropy of oxygen. You can then look in your chart, right? Go ahead and plug those numbers in. So we're just bringing down this 4 for NO. We look up NO, tells us it's 210.8 joules per mole Kelvin. So we're going to plug that in. As you can see, their units, they just have as joules per Kelvin. Well, that's because this was moles, right? This was 4 moles of NO times joules per mole Kelvin, right? Our moles end up canceling. So we're left with just units of joules per Kelvin. So they plug that in for S of our NO. They plug that in for our S of water, our ammonia, our oxygen, right? You would just plug everything in accordingly. Make sure you add all of the products together and then subtract all of the reactants that were added together. So they went ahead and solved for the product value, they went ahead and solved for the reactant value, and then they took products minus reactants. So the delta S of this reaction is 178.8 joules per Kelvin.